stop flow. And it illustrates further power of this three-dimensional stratagem, or taking spectra instead of data at a single wavelength. So take a look at these. So this is a data set. It was collected in a 0.2 of a second. It's 200 scans taken over a UV wavelength, and this should read intensity, not volts. Good. If I look at that in 2 dimensions, I see that I have a whole, and there's too many scans here. I'm going to set this number to 10. And I see that there's very noisy scans. Each one took a millisecond. And I look at that and I say, well, that looks much like an exponential. And if I want, I can fit it. So let's do that. I say it's an one exponential. So you're going to write some numbers down. So let's fit this curve at some wavelength. And here. Well, it's not quite a great exponential. There's curvature here, but the rate constant is 3.48. And the standard deviation is 0.76. Good. Now, let's go back here. And what we see if we move wavelengths, a very noisy, grassy looking thing. What the hell can you get out of that? And you look at 3 dimensions, wow, what the hell can you get out of that? But watch this. How many players are in the game? How many spectrally distinct spectra or chemicals? SVD. What would you say? How many players?
2.
Looks like 1, but looking at it.
What do you mean it looks like one?
I'm saying, well. But
This isn't something?
You're seeing something right there in both of those. I would say 2.
Well, obviously 2.
But I'm saying the computer says 1.
Flat. Yeah, well, forget what the computer says.
Right.
I'm asking you, a human being.
Yeah. Seeing 2.
These are flat.
Always...
There's nothing. If it's got a curvature, there's a species.
Right.
Now, but you did make the point, and I leave this there, and I point out, hey, the computer says 1. It made a mistake, the algorithm we have. And I surmise, I don't know it, I said, yeah, probably it's screwed up because there's so much noise in the data. However, once again, and therefore the human being is allowed to make the decision. It's not forced on you. And you say, I don't give a shit what you say. There's clearly 2 players here. I can see it, for goodness sakes. This is crap, noise. All right, so we go with this. And now I'm going to say, well, I think it's A to B. Well, we've seen it's an exponential already. So once again, we'll get better kinetics because we have lots of wavelengths. Very terrible looking noisy stuff. But if we can get the right mechanism, it'll show us what A and B look like. Boom. Wonderful exponential. The rate is 18.5. What did we get here? Wasn't 18.5.
What had it been?
I don't think I wrote that one down.
Okay. Kinetic, and the standard deviation is 0.26. Anyway, it's a much better fit.
Yeah, it's definitely a better standard.
And look at A over here. And B. Absolutely beautiful. Well, what this was...
Intensity shift and wavelength shift.
What this was or the experiment, we had some enzyme, lysozyme, in urea, and the protein became denatured in 4 molar urea. We then mixed the 4 molar urea with buffer and got 2 molar urea. That enzyme was very happy with 2 molar urea, and it refolded to its native state. Good. That's what we're seeing here. That is, here's the 2 players. Good. It's A unfolded, going to folded back to native. Red guy is unfolded. The protein is unhappy, tryptophanes are sticking out in the solvent, the intensity of the fluorescence is higher, and it's shifted in wavelength. Isn't that neat? As it folded in a small fraction of a second, it got native. The histidines got, or the tryptophanes got enclosed in the protein, the fluorescence was quenched, and it differed and it shifted. Now, effectively, you could have worked all week with experiments using a single wavelength of fluorescence and not shown what this did. And I like to do it. Here's 0.2 of a second. Ah, 2 players. Gosh, I think it's this stuff getting folded. Boom. An absolutely marvelous answer with a few clicks of a button from what looks like incorrigible data. What the hell are you going to get out of that? Good. Now,
Okay.
another one related to this.